Good morning, everyone. It's my pleasure to be able to attend this meeting. My name is Yang. Today, I would like to present my paper, PSG, Local Privacy Preserving Synthetic Social Graph Generation. And this work is done by Yang, Hongyu Huang, and Yantao Li. My presentation will cover the following aspects: Introduction, problem statement, system model, privacy protection mechanism, synthetic network generation, performance evaluation. Concluding. Social graph contains the user's social relationships. In order to obtain social graph, a server requires users to submit their relationships. Obviously, the information is sensitive, which brings a serious risk to users' privacy, and most of the existing works generate the sensitive graph in a randomized way. The attribute values of the social network synthetic graph judged by the random model is indeterminate. We cannot obtain values that are similar to the attributes value of the original social graph. In order to generate a synthetic social graph in a privacy-preserving way, we need to solve two problems. First one, how to find a message to add the noisy to the degree vector for the user to privacy users' protection. Second, how to generate a synthetic social graph based on sensitive information submitted by users. To address those issues, we propose PSG scheme in this paper. Now, we introduce the parameters required for the PSG method. We consider social network with n users. We model the network as an undirect graph G, where V and E indicate sets of users and their correlations, respectively. The server divides all users into k disjoint groups, denoted as R. We assume that user Vi in the case group has number of friends gamma I, and the range of users Vi lost in the case group has a valid range. PSG contains a three-stage process to generate the social graph. In the first stage, the server randomized divides all users into k disjoint groups. Then, the server distributes those groups to all users. Each user computes friends in each group and then obtains degree vector. In order to protect the local privacy, each user perturbs the vector before submits to the server. In the second stage, the server reconstructs the group and distributes to all users again. At this stage, the number of groups and members in each group are different from the first stage, but they do the same as the first stage. In the last stage, the server computes the degree of each user and assigns him with some other users as his friends. This assignment runs iteratively until all users have enough friends. To this end, the server builds the synthetic social graph. In order to generate a synthetic social graph in a privacy-preserving way, we need to find a method to add the noise to the degree vector for the user privacy. Specifically, we use the differential privacy as our privacy model. However, the degree of each node in the graph must be non-negative and less than the number of nodes. Thus, simple use Laplace distribution may generate out-of-bounds noise. Hence, we design randomized mechanism that satisfies differential privacy and outputs degrees in the valid range to address the first problem. We adopt the tracted Laplace algorithm to control the noisy value within the value range. Specifically, the user calculates the number of friends in each group according to receiver group results to form a degree vector, and then uses the truncated Laplace algorithm to add noise to the degree vector. Finally, the noise degree vector is returned to a server for data processing. Our second problem is to generate synthetic social graph based on degree vector submitted by users. Suppose we have one metric to measure the utility of collecting age, and then we can generate the synthetic social graph by solving the combinatorial optimization problem. Therefore, we propose SNGCO, or synthetic network generation by combinatorial optimization to address the second problem. For the assignment problem and its variants, a large number of algorithms are proposed to obtain feasible solution close to the optimal algorithm. The greedy algorithm is the simplest and most intuitive one. According to algorithm, the server has two stages. First, the server calculates a utility matrix based on cosine similarity between nodes. And second, the server uses a greedy algorithm to generate a social sensitive graph. Specifically, in the user dividing phases, the server random divides user twice. Firstly, it randomized the user into KE groups. Next, the server collects the user noisy degree vector and then uses k-means to classify users. The optical K2 value is calculated to obtain the latest user noisy degree vector. In real life, we realize that if two people have more friends in common, they have more likely to become friends. In the same way, if the degree vectors of two nodes are more similarity, then they are more likely to be collected. After server collects the noise degree vector of users, using correlation with the cosine similarity between nodes of the metric, an utility matrix is constructed to express the possibility of collecting between users. Finally, the server builds synthetic graph. In the experiment, we select two real data sets to verify our method, Facebook and last film. To demonstrate the usability of our proposed algorithm compared with the traditional graph generation models, we focus on four aspects of utility, including the mean absolute error of clustering coefficient, modularity, adjusted Randle index, and eigenvector centrality. We first show that the mean of clustering coefficient varies with the privacy budget. We find that mean of all methods decreases as the privacy budget increases, but BTR obtains the best result in all graph generation models. As expected, BTR is an algorithm proposed for optimizing the clustering coefficient. However, our model is very close to BTR compared to others. In this figure, we use the two metrics of modularity and ARI to evaluate how well the graph models preserve the community structure. Similarity: if the mean of the modularity is smaller and the value of ARI is more higher, the static social graph is better to preserve community structure of the original social graph. We show